You know, stem cell therapy, it's one of the most exciting frontiers in all of medicine. I mean, it holds the promise to repair our bodies from the inside out. But, and this is a big but, we've been using these incredible cells almost completely in the dark. Well, let's dive into a new breakthrough that's about to, literally, turn on the lights.
I mean, just think about it for a second. We inject these powerful healing cells into a patient, maybe to repair a damaged heart or a spinal cord injury, and then what? We kind of just cross our fingers and hope for the best? We have very, very limited ways to know what happens next. Are they even getting to the right place? Are they surviving? Are they actually healing the tissue?
The promise of stem cells is absolutely mind-blowing. We're talking about the potential to regenerate damaged tissues and create brand new treatments for everything from Parkinson's and heart disease to all sorts of injuries. But there's this huge problem lurking just beneath the surface of all that potential.
And this really gets to the heart of the challenge. First off, after we inject them, a whole lot of these precious stem cells just die. Gone. Second, sometimes they wander off and end up in the wrong part of the body. And crucially, our main way of checking on them, it's through biopsies, which are painful, can cause more damage, and only give us a single snapshot in time. We are, for all intents and purposes, flying completely blind.
So here's the bottom line. We're making these huge multi-million-dollar bets on a therapy where we can't even see the players once the game has started. What we desperately need is a way to track these cells without cutting someone open, to see in real time if they're alive and doing their job, or if they're just dying off.
So how do we fix this? How do we get our eyes inside the body? Well, researchers have come up with a truly brilliant answer. A tiny, microscopic spy that's designed to go inside the stem cells and report back on exactly what's happening.
It's called the APD nanosensor. Now, at its core, it's just a teeny tiny gold nanoparticle. But the real magic, that's in its custom-designed coating. This coating does two critical things. First, it works like a secret key to get the sensor inside a stem cell. And second, it's rigged with a trigger that sends out a distress signal if that cell starts to die.
The design is just so clever, and it all comes down to this three-part system. First up, you have the key. It's a peptide called R9, and it basically unlocks the door to the cell membrane so the sensor can slip right in. Next, you've got the trigger, a sequence called DEVD that's basically a tripwire. It's designed to be cut by only one specific enzyme, an enzyme that only shows up when a cell is dying. And finally, the amplifier. Once that trigger gets cut, a little hydrophobic tail is exposed, which makes all the nearby nanosensors suddenly clump together. And that clumping, well, that's what sends the signal.
Okay, so you've got this clumping action. But how in the world does that create a signal we can actually see from outside the body? The best way to think about it is like a microscopic flare gun. It stays quiet when everything's fine, but it fires off this bright, unmissable signal when there's an emergency.
And the emergency it's looking for is an enzyme called caspase-3. People in the field call this the executioner enzyme. You see, when a cell is healthy and happy, caspase-3 is just dormant, not doing anything. But as soon as that cell gets the signal to self-destruct, a process called apoptosis, caspase-3 kicks into gear. Its activation is the ultimate point of no return. It is the most definitive sign you can get that a cell is on its way out.
And this is where it all comes together. In a healthy cell, caspase-3 is inactive, right? So the nanosensors just float around by themselves, and the special photoacoustic signal we're measuring is low. But in a dying cell, caspase-3 wakes up. It finds that DEVD trigger on our nanosensor and it snips it. Instantly, the sensors all clump together and boom, the photoacoustic signal flares up. It's this beautiful, simple turn-on system that is incredibly specific and easy to spot.
And the proof? Well, it's pretty amazing. When the researchers just mixed the nanosensors with that caspase-3 enzyme in a test tube, two incredible things happened. First, you could see the color of the liquid change from ruby red to deep purple with your own eyes. And when they measured the photoacoustic signal, a massive 22-fold increase over the baseline. Right then, they knew they had something really special.
Okay, so it works like a charm in a test tube. But that's the easy part, right? The real question is, can this microscopic flare gun actually work inside living cells?
And yep, the results were crystal clear. The researchers took stem cells, loaded them up with these nanosensors, and then used a chemical to trigger that self-destruct sequence, apoptosis. The dying cells lit up, sending out a photoacoustic signal that was 2.4 times stronger than the healthy ones. The flare gun was working, loud and clear.
But this is the moment of truth for any new medical technology. It's one thing to see a signal light up in a petri dish. It is a whole other challenge to detect that same faint signal from deep inside a complex, living, breathing system. And you know what? The answer was a huge, resounding yes. They used a mouse model of ischemia. That's a condition with low oxygen that puts a ton of stress on cells, a place where you'd expect stem cells to really struggle. And over 7 days, the signal from the dying cells increased by a factor of 4.8. That is a massive, unambiguous signal.
And just to be absolutely sure the sensor was really picking up on stress-induced cell death, they did this brilliant comparison. In the high-stress leg with ischemia, where a lot of cells were expected to die, they saw that strong 4.8-fold signal increase. But in the healthy, low-stress leg, where only a little bit of normal cell turnover would happen, the signal only went up by 2.1-fold. This shows that the sensor isn't just on or off, it's actually measuring the amount of cell death that's happening.
So what does this all mean? Why is finally being able to see what our stem cells are doing, why is that such a game changer?
What this does is hand doctors and researchers a brand new toolkit. It's non-invasive, so no more painful biopsies. It's longitudinal, meaning you can check in on the cells day after day, week after week. It's super specific because it only hones in on that caspase-3 enzyme, so you don't get false alarms. And maybe most importantly, it gives us two critical pieces of information at the same time, exactly where the stem cells are and their functional status. Are they alive and working, or are they dying?
And this isn't just about cool science in a lab. The real-world implications are profound. As the researchers themselves put it, a physician could use this technology to see if a stem cell treatment is starting to fail. They could figure out the exact best time to give a patient a second dose, or maybe change the dosage, which could dramatically improve the chances of success for that patient.
So all of this brings us to one final, really big question. For decades, we've been coming up with these incredibly advanced therapies, but we've been doing it while partially blind to how they really work inside the body. Now we have a way to see them in real time, opening up a whole new era of precision medicine. So I'll just leave you with this to think about. If we can finally see exactly what our most powerful therapies are doing, what impossible cures might now be within our reach?